right, so for our first polar area example, we're going to look at the graph r equals 2 plus 2 sine theta and the area that is bounded within it. So what's super helpful to do first off the bat is identify what type of graph this is. So if these, the shift and the amplitude match, that means that it's going to just touch the x-axis, so it's going to be a cardioid in polar form. And since it's a sine theta, we know that it will have y-axis symmetry. That's what it will be centered on, so to speak. So it's always good to kind of like have a visual before you try to actually sketch anything. So I'm going to come over here. I'm going to try to do a quick sketch. So usually I just stick with 0, pi over 2, pi, 3 pi over 2, and 2 pi to make my sketch. So if we plug in 0 for sine, we're going to get 0 plus 2. So I'll stick him here at 2. And then if I plug in pi over 2, sine is 1 there. So that's going to be a 2 plus 2. So that's actually going to give me 4. Might need to make my line a little bit longer. Okay, there's the first part. Now if I find sine at pi, that's just going to be 0 again, so I'm left with 2. And then if I look at 3 pi over 2, sine's a negative 1 here. So negative 1 times 2 is negative 2 plus 2, so that's where the 0 is coming in. Going into 0, and then of course when we go to 2 pi, it's going to go back out to 2. So this is our graph that we're visualizing, and what I'm telling you now is that I want you to find the area. So we want to find all of this area enclosed by this cardioid. Now, there's going to be a lot of ways to do each of the problems we look at with area, so I'm going to start with that. There is no just single way to do it, especially with the, fluidity of polar coordinates and how there's multiple representations for a single coordinate or angle. There's so many coterminal angles, so just know up front there's a lot of ways to do these problems. I'll show you the 2 most common ways whenever we work on them, but obviously it's not restricted to that interpretation. So first of all, let's remember our formula. So area, when we're working with area of a polar graph, is 1/2 integral from alpha to beta of whatever your r squared is in terms of theta. Okay. So in this case, let's talk about it. If we're talking about the entire graph here, right, we started at 0 and it took all the way to until 2 pi to actually complete the graph. And that's something a lot of times I'll also try to remember right at the start is like, what's the, how long does this graph take to complete a full cycle? And most of them, if you remember, are 0 to 2 pi. There's 2 cases where it would be pi, and we'll get to some of those in a bit. So 0 to 2 pi is what we would need to actually complete the full graph, and so that's giving us the bounds that we will end up using for our alpha and our beta. R is going to come from the actual function itself. The most common mistake here is not remembering that the definition of this area formula coming from pi r squared means that we're squaring that function. Okay, so let's go ahead and try to put all of this together. So the area would be 1/2. We have to go from 0 to 2 pi. The r function is 2 plus 2 sine theta. So that's what's being squared. And then we're deriving with respect to theta. Okay, so that's probably the most intuitive way to do these up front. What we'll start doing a lot of times is we're going to do the same problems but with the help of symmetry. So what I mean by this is, okay, well, we just found this whole inside area going all the way around the circle, and I have a cool applet to show you guys tomorrow on how to do this. So we did the entire rotation all the way going from 0 to pi over 2 to pi to 3 pi over 2 and then back to 2 pi. The fact that most of these graphs have at least one line of symmetry, if not more, is something that we can greatly take advantage of with polar area. So for instance, we noted that this one is symmetric with respect to the y-axis. So what this means is I could actually take a look at maybe just part of this graph at a time, and then knowing that it's symmetrical, simply multiply whatever this integral is by 2, and then that nicely kind of addresses the 1/2 built into the formula. So let's give this a shot. So if I'm trying to get just half of the graph at a time, just remember that at 0 we actually started here at 2 and then went up there. So from 0 to pi over 2, it's really just this chunk here. So I wouldn't want to say, okay, well half the graph, that's half of 2 pi, so 0 to pi, because 0 to pi is actually this chunk, and that is not just half of our area. Okay, so you need to be very careful about how you interpret your bounds here. So 0 to pi over 2 isn't exactly half. In fact, it would be very nice if I could kind of work backwards from 2 pi down to 3 pi over 2. And thinking of it in terms of a negative rotation, I might just think of this as a negative pi over 2. Oops. So using symmetry, first of all, I'm going to have to change my bounds, right? So I'm going to try what I was just talking about of negative pi over 2 to positive pi over 2 to get this right half of the graph. The r squared would still be the same. The big difference is we do 2 times all of this, right? And when we do that, these nicely cancel out. So this really comes into play when you're doing multiple choice problems, because obviously most of us will probably go to this first setup as an intuitive choice, but a lot of times in multiple choice, you won't see a 1/2 out front, and it's because they've done something with symmetry that allows them to kind of undo that constant multiple, right? So then you could see an answer choice that instead has something along these lines. Now, even this is not the only way we could have used symmetry. We focused on the right side of the graph because we tend to start at 0 a lot, but you also could have started kind of in the middle and done instead the left side of the graph, right? So let's say I had started at pi over 2, and then I could have just gone to 3 pi over 2 without involving any negatives whatsoever. So you could actually do this same thing, right? Still doubling it and thus undoing that 1/2, but used bounds of pi over 2 to 3 pi over 2. And this all should give you the same exact area. Okay, and we'll verify this in class. What we're actually going to do in the next video is figure out how to find this area by hand. We're going to be doing a lot of trig stuff, and squaring it makes it a little more complicated. So in terms of doing an integration by hand, right, if you're using calculator, these are fine. If you're not using a calculator, it's really nice if one of these bounds is something with a 0. So we're going to go and actually do this one by hand in the next video.